Hello class, and thank you for watching. In the second part of 3.5, we're going to go over reflections and dilations. We'll begin by looking over vertical reflection, and we'll start by the notation of how to reflect a graph vertically. So the notation for that is that we'll have this function g, we'll call it g, and it's going to look exactly like f of x, with the exception that we're going to multiply f of x with a negative value. This notation here will result in flipping something across the x-axis. So that would make our x-axis our line of reflection. So we want to flip our line across this yellow line. Or our graph, I'm sorry. We want to flip our graph across this yellow line. So the point that we have here, which is located at 1, 1, flipped across the yellow line would be at 1, negative 1. And the other point, which has the coordinate of 4, 2, flipped across that line would be at 4, negative 2. So this right here would be our reflection. Now, if you look at the coordinates, pay attention specifically to the y values. Notice that the y values are the opposite of what we originally had. From positive 1 to negative 1, positive 2 to negative 2. This notation is telling us essentially that for every x and y value that's on the original function, then the point x times negative y is going to be on the graph of the reflection. Okay? So if I look at the table, well, what does that mean? That means, again, that my y values are going to simply be the opposite of what they currently are. So let's say I have a table representation of my function, where these are the inputs and output values. And I want to create, again, this function, which, again, this right here should be g of x, not f of x, for g. Well, this notation right here, as I mentioned earlier, is going to result in simply multiplying all of your y values by a negative 1. So your x values are going to stay the same as 2, 4, 6, and 8, but your y values are going to change to negative 1, negative 3, negative 7, and negative 11. So a reflection across, let me zoom out, a reflection across the x-axis, which again is denoted by this, is going to result ultimately into simply switching your y values to the opposite sign, and hence it will flip it across the x-axis and make the x-axis your line of reflection. So simply doing that with any coordinate will result in the reflection of your image, of your pre-image. Let's now continue with horizontal reflections. The notation for a horizontal reflection still involves a negative sign, but the negative sign, g of x, let's call it g of x, not y, will be done to the x this time. So this time we're not multiplying f of x, we're multiplying only the variable x, so the input value. This is going to result in reflecting the graph across the y-axis. So that's going to make the y-axis the line of reflection, and our points with the same coordinates as the previous example, 1, 1, and 4, 2, will now be flipped across this yellow line, placing them at 1, negative 1, 1, and negative 4, 2. So your graph will look like that. Now what I want you to pay attention to on this example as well is notice how in this situation your y values are now the opposite of the pre-image. So the reflection across the y-axis, again a negative x right there, it's going to result that for every xy that's on the graph, so every coordinate that we have here on the graph of the pre-image, then the image, the reflection, it's going to have the opposite x coordinate but the same y coordinate as a result, like I said, in the reflection of f of negative x. So if we apply this idea to a table, like in this function here, apply that concept to this table, we want to perform this reflection, then that would mean that we would simply switch all of my x values, since we're going to reflect it across the y-axis, switch all of the x values to the opposite number. So positive 2, 4, 6, and 8 all become negative, and your y values will stay the same. Let's now move on to vertical stretching and shrinking graphs, okay, so dilations. So let's assume again f is a function, but this time we have this value of c that's going to be a positive real number. Now if the value of c is a number greater than 1, then the notation that y equals c times f of x is going to be the same thing as the graph of x, but it has been vertically dilated to a stretch, has been vertically stretched by multiplying each of its y values by this value of c. So if you look at the example that I have right here, okay, in this example I have right here on the left side, let's say that I have this coordinates at 1 where the y value is 2, and we're going to multiply this function, again this f of x, by this value of c. And let's say that the value of c is a number bigger than 1. Let's say it's equal to 3, okay? So multiplying, in order to stretch this, it's going to again be 3 times as tall as it currently is. So right now, the height of this arch right here has a height of 2. Multiplying the function, the entire function by 3, is going to result that the y values, or in terms of this height, is going to be stretched to 3 times its original size. So 2 times 3 is equal to 6. So this will now have a height of 6 units. So the coordinate changes from 1, 2 to the coordinate of 1, 6 by multiplying, yet again, f of x by this value of c. So this c again acts again like a outside scalar, again a multiplication value, to your y coordinates. So this notation means to multiply your y values by c. Now if that value of c is less than 1, then the opposite just occurs, that instead of shrinking it and making it taller, stretching it and making it taller, it's going to do the opposite, and it's going to shrink it by multiplying yet again each one of its y values or y coordinates by that value of c. So let's look at 2 examples of this, okay? One making it bigger, one making it smaller. So in example 11a, we have that we want to draw the graph of h, which is going to equal to the same graph as f, but it's going to be half the size, okay? So we're going to multiply all of our y values by half. So if I look at the corresponding y coordinates, so right here, this point here has an x coordinate of -6, but the y coordinate is -4. So we're going to go half that distance. So instead of going down 4, we're going to multiply that -4 by half, and we're only going to go down 2. So from this x-axis, we're just shrinking the distance from this point, from this line here. So the first point is going to simply go down 2 instead of down 4. Notice that the x value doesn't change. Now, since this point is on 0, well, getting half of 0 is still 0. And the same thing with this one right here. Those x coordinates are negative and positive 2, but they have the same y coordinate of 0. And that's what we're focusing on, the y coordinate. So since this point has a y coordinate of 4, the x value is 0, but the y coordinate is 4, instead of going up 4 units from the x-axis, multiplying again f of x by 1/2, it's going to multiply this y value of 4 by half. So we're only going to go up 2 units. Half of 4 is positive 2. And then the same thing with this last point here. This last point has an x value of 6, but the y value is -2. So half of -2 is -1. So this is only going to go down half the distance. So the graph will look like this. Now, if we're multiplying by, let's say 2, let's not make this into 3, let's say it's a 2. then multiplying all of your y values by 2 is going to make it stretch. It's going to make it taller. So this notation, because it's 2 times f of x, means to multiply your y values or your y coordinates by 2. So the y coordinates are the same as the previous graph. It's the same function f. So the y coordinate of -4 is now going to be -8. The y coordinate is 0, is still going to be 0, because again, it doesn't matter. 0 multiplied with anything is still going to be 0. The y coordinate on this point here, which was 4, is now going to be +8. And the y coordinate on the point that we have here on the right, which is -2, multiplying that by 2 is now -4. So when I connect those dots, the graph, again, as you see, has been stretched. So the idea behind this, again, correlates directly to what we're doing. Since we're doing this multiplication to f of x, and f of x is essentially the same thing as y, our y values are what's being affected. Just like with our vertical shift. Adding the value of k outside the parentheses is affecting the y values. So the same thing here. Having this number that we're multiplying our function with is on the outside of the parentheses, not to the x. It's going to affect the y coordinates. And simply multiplying by that value would automatically stretch or shrink the graph to its appropriate size. Let's now look at a horizontal. What does it look like when we do it the other direction, horizontally, left and right? The notation obviously has to be different, because we can have the notation, same notation, mean two different things. And the notation to do something horizontally is going to affect the x coordinates. So the multiplication of this positive value of c is going to be inside the parentheses, as you see again in both notations. Now, here, if the value of c, again because it's an x, is going to be backwards. If the value of c is bigger than 1, then it's not going to do the same thing as the previous one with the vertical one. Instead of stretching it, it actually shrinks it. It shrinks it because instead of multiplying our x coordinate, we are going to divide the x coordinates by this value of c. So if that value is less than 1, still positive of course, but less than 1, then that's going to result in a stretch, because again, we would be dividing all of our x coordinates by c. So since the numbers again are less than 1, that's going to be some decimal value or a fraction. And to divide by a fraction or a decimal, again, ends up multiplying. If you have a fraction, it's probably easier, more convenient to look and see the number as a decimal, because you simply have to multiply by the reciprocal of that value. Which if it's a number like 1/4, 1/3, 1/2, you simply have to multiply by the denominator, and that's how you divide by that fraction, as you'll see in the examples right here. So you see right here, what's going on to our coordinates here is that the x values, again, because we're going to do this horizontally, the x coordinates are going to move either closer to the y-axis or further away from the y-axis. If the number is bigger than 1, like I said, it'll move closer. So this x coordinate here in blue will move closer and become this x coordinate right here in red. And for a stretch, the value of c would be some decimal value less than 1, and it's going to stretch it outside. So it has this x coordinate originally here in blue, and it's going to stretch out to this new x coordinate right here in red. You'll notice that the y coordinate doesn't change. That stays the same. Notice that both functions have still the exact same height. So let's look at this example, the examples of this. Okay, so here we have the function f, and let me zoom in on a. Let's focus on that one first. And what we want to do is this right here. We want to get f of 2x. Now I know that we have, again, an inclination to just simply multiply the x values by 2, because that's exactly what it says, but we're not going to do that. Very much like with horizontal shifts, we're going to do the opposite of what actually it states in the notation. So instead of dividing the x, instead of multiplying the x's by 2, this is going to divide our x coordinates by 2. Okay, so we do the opposite operation. So looking at all the x coordinates, we're going to divide all of those by 2. So starting with this point right here on the left, okay, -4. The x coordinate, again, is -4. The y value is 0. Again, the y value doesn't change, so I'm just going to simply slide it inwards by half. So -4 divided by 2 is -2. So that would put that position right there. This point up here has an x coordinate of -2. And again, I'm just going to slide it closer to the y-axis. So it's not going to change height. So right here, -2 divided by +2 is -1. So that's going to put that position here at -1, 4. Now this x coordinate doesn't change because that x coordinate is 0. 0 divided by 2 is still 0. But the second x coordinate has an x coordinate of 2. This point right here has an x coordinate of 2. So 2 divided by 2 is 1. So that will keep it there. And yet again, I know I sound like a broken record, but my y value is not changing. And then finally, the same thing with the last one. 4 divided by 2 is 2. And the y coordinate is going to stay at 0. So this is what the transformation will look like if I multiply the x coordinates by 2, if I have f of 2 of x. Now let's look at if I have the reciprocal of that, if I have 1/2. So again, we're not going to multiply the x coordinates by 1/2 because again, like I mentioned earlier, we have an inclination of just doing exactly that because it says to multiply the x's by 1/2. But that's not really what's going on here. It's affecting again our x-intercepts, figuring out again what values of x equal to the original y values. So what we have to do is essentially solve an equation. So the inverse operation, the multiplying by 1/2, is to divide by 1/2. So we're going to do that to get the correct coordinates. So divide our x coordinates by half. Now here's the problem. How do we divide by half? Well, dividing by half, because it's a fraction, is the equivalency of multiplying by the reciprocal of this number. So if I flip this number, the reciprocal, I'm going to end up with the number 2 over 1. So to divide by 1/2 is the exact same thing as simply multiplying by 2. So that's how I divide by a fraction. You flip the number and multiply. So if I look at these coordinates, -4 again is the coordinate right here. Dividing that by 1/2 is going to become 8. This coordinate up here is negative, has a x coordinate of -2. Dividing -2 by 1/2 is -4. 0 stays in the same location because again it has an x value of 0. This next point has a x value of +2. This coordinate has an x value of +2. So 2 again divided by 1/2 is 4. And then the last point has an x coordinate of 4, and 4 divided by 1/2 is 8. And yet again, the y value does not change in this example because we're not doing anything on the outside of f of x. We're not adding anything to the function f of x, and we're not multiplying any number in front of f of x, so the y coordinates are not being affected. So as you see, this resulted in a horizontal stretch because now we're further away from the y-axis. So when the numbers are in the inside and we're doing something to the x, that's going to affect us horizontally. And for dilations, we're either going to move closer to the y-axis or further away from the y-axis when we divide those x coordinates by whatever number we have there, by whatever scalar we have for x. And like with vertical, and very similar with vertical dilations, simply doing the operation, like in this case dividing, automatically will shrink or stretch the graph appropriately and give you again where the position is going to be. So let's apply this concept again to the coordinates, and let's see how well we understood this. Because we apply it again to the coordinates, it won't matter if we're given a graph. We can just make our own table and apply again the appropriate transformation, and then plotting them will automatically draw us again the appropriate graph and the appropriate transformation. So pause the video, see if you can figure out what the x and y values are to A, B, C, and D, and then come back and check. Okay, so let's check again your responses. So for the first notation here, because the 1/3 is on the outside, that is going to affect the y coordinate. So 1/3 of f of x means we're going to multiply the y values by 1/3. So the x values do not change. They're going to stay as -6, +6, 18, and 24. But the y coordinates are going to be 1/3 of what they originally are. So 1/3 of 3 is 1, 1/3 of 6 is 2, 1/3 of 9 is 3, and 1/3 of 12 is 4. Let's now look at the second example. For the second example, that 1/3 is now on the inside. So that is going to affect the x coordinates. But instead of multiplying the x coordinates by 1/3 like we did with the previous table, on the y values, we're going to divide the x coordinates by 1/3. So over here we multiplied the y coordinates by 1/3, and now that the 1/3 is on the inside, it's going to affect the x coordinates first of all, but instead of multiplying like we did in the previous table, we're going to divide. So our y values are going to stay as 3, 6, 9, and 12, but the x values are going to be divided by 1/3. So -6 divided by 1/3 is -18. 6 divided by 1/3 is 18. 18 divided by 1/3, that is 54. And 24 divided by 1/3 is 72. Now again, if you're wondering how do I get those numbers, how do I divide by 1/3, all you're doing is getting any x value. Let's look at the last one. How do I get 72? I got that 24, and to divide by 1/3, I'm really simply flipping this number to 3/1, which is just 3, and then multiplying instead. That's how you divide by a fraction. Flip the number and multiply. And since these numbers are under 1, when I flip it, it just becomes a whole number. So 24 times 3 essentially. That's how I ended up with 72. And the same thing with 18. 18 essentially gets multiplied with 3, and that's how you end up with 54. Let's now look at the last two examples. So in the last two examples have to do with 3. And just like with example C, notice that the 3 on this one is on the inside. So that's going to affect, yet again, the x values. So our y values are going to stay the same. Let me get, there we go, 3, 6, 9, and 12. And instead of multiplying the x values by 3, we're going to divide them by 3. So looking at the original table up here, dividing those three numbers, I'm sorry, wrong one. This is the right table. We're going to divide these x coordinates by 3. So -6 divided by 3 is -2. +6 divided by 3 is +2. 18 and 24 divided by 3 are 6 and 8 respectively. So there's your table for letter C. Now if that 3 is on the outside, that's going to affect the y coordinates. So your x coordinates are going to stay the same, -6, +6, 33, 18, and 24. But your y values are now going to change. And for the y coordinate, we do the notation that we have. So since this is 3 times f of x, we're going to multiply our f of x values, which again are our y values. We're going to get these f of x values and simply multiply them by 3. So 3 times 3 is 9, 6 times 3 is 18, 9 times 3 is 27, and 12 times 3 is a total of 36. Let me make sure that I got, yes, let me zoom out. Okay, yes, I did multiply these numbers by 3. So 3, yes, they're all right, okay? So there. This is how you dilate horizontally and vertically. And now finally, let's go over how do we perform all these transformations, let's say at once, okay? Not individual, not the shifts, the reflections, and the dilations individually. Let's say we have a function that's going to transform another function f by performing again multiple transformations. Well, to do this, there's two simple steps. First, focus on your horizontal transformations, okay? Focusing on the on the horizontal reflection and dilation, and then the horizontal shift. And the best way to organize your work is to look at a table of values so we know what we're doing to those coordinates. So I'm going to do this horizontally. So I have x and y values to f of x. And the coordinates are -4, 0, -2, +4, 0, 0, 2, -2, and the last one is 4, 0 again, or +4, but y value is 0. So all I've done is just simply figured out the coordinates again of those 5 positions from left to right, okay? I just did the table horizontally. So we're going to start by first looking at the horizontal shifts, okay? And like I said, we're doing a combination of two things. We're going to dilate it horizontally by a factor of 1/2, and we're going to shift it also because we have this x minus 1. We're going to shift it afterwards, okay? Now recall, when we're doing horizontal transformations, we're going to do the opposite of these notations. So we're not going to multiply all the x values by 2. We're going to divide all of the x values by 2, and instead of subtracting the x value by 1, we're going to add 1. So opposite operations. So all of our x coordinates, let me do it right here in red and blue, will be divided by 2, and then that answer will be increased by 1. So we're going to do those two steps to create this new table for the x and y coordinates of h. So let's start by doing that. So let's start with the x value. So we're going to start by getting -4 dividing it by 2, which is -2, and adding 1 to it. So that gives us a total of -3. We're now going to do the same thing with -2. -2 divided by 2 is -1, and -1 plus 1 is 0. 0 divided by 2 is 0, plus 1 is 1. Now with 2 divided by 2 is 1, and 1 plus 1 is 3. 1 plus 1 is 2. And then finally 4. 4 divided by 2 is 2, plus 1, 3. Okay, so now, oh, hold on. There's an error here. That should be -1. I did the math wrong on the first one. -4 divided by 2 is -2, and -2 plus 1 is -1. Okay, now let's focus on the vertical transformations. The vertical transformations are on the outside of the function of the notation f of x. And we have also 2. We have this 2 in the front, so this is 2 times f of x plus 3. So we want to do two things to the values of f of x. We want to multiply them by 2 and add 3 to that. So times 2 and add 3 to all of those values. So starting with 0, 0 times 2 is 0, plus 3 is 3. And now 4. 4 times 2 is 8. 8 plus 3 is 11. Again, 0 times 2 plus 3 is 3. So I know that the last number is also going to be 3. because it's the same value as before and I'm doing the same operations. So now negative 2. Negative 2 times 2 is negative 4, and negative 4 plus 3 is negative 1. So if I plot those points, that's going to create the transformation for h. So negative 1, 3, 0, 11. So that's going to be up there, all the way up there, one higher. 1, 3, 2, negative 1, and then 3, 3. And there is your transformation. Okay, so let's now look at example 16. I don't know what to be, but 16, okay? So just similar to number 15, all we need to do is, again, recognize the notation and what it's going to affect. So the inside part is going to affect our x values. But again, instead of doing the operations that are indicated of adding and multiplying, we're going to do the opposite. We're going to do the opposite of multiplying by 1/4, and we're going to divide those values by 1/4. So we divide by 1/4, and instead of adding 1, we're going to subtract 1. So let's do that with these values. Okay, so let me make a table underneath x and h. And let's plot the points. So dividing all of these numbers by 1/4 is the exact same thing as essentially just multiplying them by 4, because we're going to flip the number and it becomes 4/1, and we change the operation to multiplication. So if I do that, that's the same thing as dividing by 1/4. So negative 6 divided by 1/4 is negative 24. Negative 24 plus, so that's negative 24. Negative 24 minus 1 is negative 25. Now moving on with negative 3. Negative 3 divided by 1/4 is negative 12. Negative 12 minus 1 is negative 13. The next number is 0. So 0 divided by 1/4 is 0, and 0 minus 1 is negative 1. Sorry. Negative 1. There we go. And now 3. 3 divided by 1/4 is 12. 12 minus 1 is 11. And then finally 9. 9 divided by 1/4 is 36. And 36 minus 1 is 35. And now we can move on to the y values. So our y values, we're doing two things yet again. We're multiplying our y value or f of x by 1/3 and then subtracting 2. So that's exactly what we're going to do to the y coordinates. We're going to multiply by 1/3 and subtract 2. So starting with negative 9, negative 9 times 1/3, that gives us negative 3, and negative 3 minus 2 is negative 5. Now negative 6 times 1/3 is negative 2, and negative 2 minus 2 is negative 4. 3 times 1/3 is 1, and 1 minus 2 is negative 1. 9 times 1/3, well, it's the same as this number, but just positive. So positive 3 minus 2 is 1. And then 12 times 1/3 is 4, and 4 minus 2 is 2. So there is your table for the graph of h. So again, just to recap this part right here, remember again, the key thing is the x values. Those are the ones again that you have to recall that you're doing the opposite operation now, okay? Now to perform a horizontal shift with a horizontal dilation, you have to separate again the two notations like the way I have them right here. So for example, if I was to give you an example, ignore that we have the 1/3 and the 2, for example, okay? And let's say I have f of 1/4 x plus 1/4, okay? This is not going to be the way that you want to look at the problem to determine what the horizontal and the horizontal dilation and a slide translation are going to be. You want to separate again this multiplication here and factor out this number so you can see by how much you're shifting the graph. The multiplication of this x, again without the parentheses, without being factored, skews what the notation means and how we're going to shift this appropriately. So in those type of situations, you want to factor out the common factor, which again normally is going to be just whatever this whole number is. And this gives you an idea, the better notation to determine again how we're going to do the horizontal shift. Okay, well, it should be to the left, the horizontal shift. Okay, so it's very important that there's always a parentheses around the x and this scalar that we're multiplying by. If there isn't, then just factor that common factor. It's set up again so that this value and this value have a common factor, which again is simply going to be whatever this number is. Factor that number out, and then you can separate it, and then you know exactly what to do to your x's. Divide your x's by 1/4 and subtract 1. Okay, well, that concludes again the second part to this. I hope you found this video helpful, and like always, I appreciate you watching, and I hope you have a great day. Goodbye.